Good afternoon. Let us introduce our project, which is about molecular properties estimation. Firstly, we will describe the problem in detail. A molecule, to put it simply, is a system of atoms and bonds between them. Molecular properties include the chemical, physical, and structural properties. In our task, we will explore the physical energies of molecules. This feature is very important in material science, quantum chemistry, drug discovery, etc. The total energy of a molecule can be calculated as a sum of the energies of the atoms of this molecule. There are direct calculations for this, but our goal is to reduce the time and cost of these calculations. Our dataset includes descriptions of molecules with the ID in string smiles format. The other features are numerical. You can see their means and derivatives on the graph. Smiles is a special string type for molecular representation. For example, there is a scheme type representation of the molecule and its corresponding smiles beneath.
So we need to try smiles string in some way, and this is not an easy task. So we did some research and several distance methods, for example, simple statistics-based methods such as 1 grams and 2 grams that we are going to use. Graph-based analytics, because molecule can be presented as a graph that you can decode from smile string, and you can analyze this entity instead of string. And also you can analyze the string by itself by using state-of-the-art NLP methods, such as transformer neural networks or long short-term memory neural networks. Firstly, before we start analyzing the featurizing methods that we have used, I'd like to say something about metrics, because again, we're solving 16 regression tasks. So we do train separate models for each of the tasks, and we do measure average of mean absolute error for all the tasks and consider this as our metric. And also there are some results related to predicting these properties for this particular data set. And long story short, mean absolute error less than 0.02 is considered okay. So we have aimed for the threshold. So we tested 3 features. So first one is 1 grams featurizing, and this is basically the calculation of frequency of symbol appearance in the smile string. And at the end, we have 15 dimensions, and you can see the sample at the top right corner. So the value of column H for the first row is 4. So that basically means that molecule corresponding to the first row has 4 hydrogen atoms in it. So we used some baseline simple models, linear regression, Canar's neighbors, and random forests, and we've compared all the features with these models. So linear regression doesn't have it, does have a better result. Canar's neighbors and random forest have acceptable result. So 2 grams method. 2 grams methods basically have the same logic as the 1 grams, but we're calculating frequencies not of symbols, but the pair of symbols. Again, you can take a look at example at the top right corner. And we have total 58 dimensions, and you can see the results are a lot better. For linear regression, it's getting better, and for KNN random forest, we've beaten up 0.02 threshold. So the next method is circular fingerprint method, and basically this method incorporates graph information, and we actually implemented it. We've used it implementation of this method from DeepChem library. Yeah, it hashes the information about graph relations in the molecule into some into a vector of fixed size. So the results are quite good. again, we've beaten 0.02 threshold. And so the last two featurized methods are quite good, and we've make a direct comparison between them. Um, yeah, and we've fine-tuned models, and as far as you can see, the random forest with big depth works well for circular fingerprint method and for 2-gram method. And Canera's neighbors method works well for circular fingerprint method and quite acceptable for 2-grams method.
So as you can see, we've tried many different models. As a baseline, we've used linear regression, and as you can see, it yielded not a very good score, but as a baseline, it is a key. Our three best models are k-nearest neighbors, random forest regression, and decision tree regression. So the quality of the k-neighbors model and random forest model are basically the same. But random forest was a little bit more stable, so we think that even though it yields a little bit worse score, it is still a very good model and the best model in our testing. Next slide, please. So as you can see in the bottom right corner, we have a table from the paper called Molecular Net and Benchmark for Molecular ML. So with the results of the testing of different models on the dataset that we've used, QM8, their best classical ML model was kernel-rich regression, and as you can see, it yielded a lot worse score than our models did. So our random forest model yielded a score of 0.079, and their kernel-rich regression yielded a score of 0.097. This means that our model is produces better results, and this validates our efforts, and this means that our model is actually beats the state-of-the-art techniques. So thank you for your time. That's it. If you have any questions, feel free to ask.